So today we're going to continue talking about groundwater, which we talked about last time from the perspective of groundwater flow and all the characteristics. And I introduced you to the topic of organic contaminants in the subsurface, and that's going to be the focus of most of today. We'll talk about organic contaminants in general, and especially we're going to spend a little bit of time at the beginning talking about what I introduced at the end, non-aqueous phase liquids, which are a particularly pesky problem. They're things that get introduced into the subsurface and don't dissolve very well in water. It's not that they don't dissolve at all, they do, but not very well. So they move in their own sort of ways. Now we'll talk about some other organic contaminants. There are a few examples here in Hawaii. And then for the latter part, we'll talk about remediation methods. And we'll talk about a few different methods, but I want to focus on some of the permeable reactive barriers, which are really useful for organic contaminants. So if you remember last time we talked about NAPLS as being a term that means non-aqueous phase liquids. And those NAPLS in the subsurface can either be more dense than water or less dense than water. So when they're more dense than water, they're called DNAPLS, and they will flow into the subsurface to the bottom of an aquifer and then distribute on the basis of whatever the shape of the substrate or the impermeable bed at the bottom of that aquifer is. Whereas LNAPLS, or sometimes just referred to as NAPLS, they'll flow on the top, they'll float on top of the water table. Think oil and vinegar salad dressing or something. And so you can get into situations where this stuff follows the flow direction of hydraulic head or whatever shape the aquifer top has, whereas this stuff can be directed by the shape of the bottom of the aquifer, which is based more on geological structure, and as is shown in this diagram, can migrate itself into cracks and become persistent. And as we'll see, this stuff here, which sits at the interface between the vadose zone and the phreatic or saturated zone, has its own set of difficulties, especially if the water table is moving up and down. As the capillary fringe becomes really important, and the ability to volatilize into pore spaces also becomes really important. So this is something that's important to consider, which is that in a system with non-aqueous phase liquids, and this could be D or L, doesn't really matter which one, we have to consider four kinds of associations of those chemicals. They can be by themselves, sitting in a pool of material in the subsurface. They can be stuck onto soil particles, sometimes displacing water in both the vadose and the saturated zone. They can partially dissolve in water and distribute with water flow, and they can volatilize into air. And once this chemical gets into one of these places, they can also directly exchange, so that we oftentimes see contaminations that have non-aqueous phase liquids becoming very complicated, involving all parts of the soil column. And even if one part is easy to clean up, not all parts are. So this is an example from perchloroethylene, which I showed you a plume of last time, where you can sort of see this is stuff that's denser than water. And so this is like unsaturated zone and saturated zone. That's, you can see the water table here. But within the subset, even in the subsurface, even in aquifers, we can sometimes find areas in the soil that are impermeable or less permeable to fluids. And so that's what's happened here. This PCE contamination has sunk through the water table and it's perched on this material that doesn't really want to let water or fluids, in this case perchloroethylene, flow through. And so from this kind of relatively high up in the aquifer setting, it can do two things. It can partly volatilize and send chemicals back up. And this is what this orange zone is kind of trying to indicate. It can slowly dissolve in water and be distributed with the groundwater flow. That's what this pinkish thing is. And it can distribute its way slowly through the aquifer to finally reach the bottom of the substrate. And each one of these different places has its own complexities. So in general, when we think about contamination in the subsurface, and this is an example of an underground storage tank, which we talked about last time, is commonly being leaking. This will leak materials into the subsurface. It will contaminate the pore spaces of the vadosome and then reach into the subsurface. And oftentimes there isn't just one chemical here, there's a mixture of chemicals. And so it's useful to understand, even if we categorize the chemicals generally as NAPLS, we want to know, well, how soluble in water are they? How volatile in the atmosphere are they? So that we can understand the individual chemical partitioning between staying in this plume, coming into the water and distributing, or getting into soil and making the vapor pressure and coming back out. And so this kind of diagram is useful. This is the solubility in water. There's a log scale. And this is the vapor pressure, again, in a log scale. And there's some chemicals on there. And what you see is that the NAPL field generally lower solubility, but not zero, right? And some of them have low vapor pressure, some of them have high vapor pressure. So for instance, this example from here, this has a relatively high vapor pressure. It doesn't like to dissolve in the water, but it doesn't mind evaporating. And so that affects the contamination dispersal. We also have, I mentioned this term last time, and I want to remind you, there's another kind of chemical that we call a VOC, which stands for volatile organic carbon. Now, volatile organic carbon compound will usually have a relatively high vapor pressure. And these VOCs can be divided up into two categories, ones that are both volatile and soluble in water, and ones that are volatile but not so soluble in water. So we're going to find them in different places in the subsurface. This is just a table with aqueous solubility along this axis. Again, it's a log scale showing you there's a big range of variabilities. There's some common D NAPLs and L NAPLs. PCBs, which we've talked about before, polychlorinated biphenyls, they're really low in solubility. They pretty much just sit in place. They're also fairly low in volatility. And so that kind of contamination is something that is remediated by attacking the material in place. But you can see all these various other chemicals, and it's not important to remember their names, but all of these things, DCE, TCE, PCE, we're going to talk about them later when we talk about permeable reactive barriers. These are halogenated hydrocarbons that can be disrupted and decomposed in the subsurface, but having them encounter a reactive surface. These things all sink below the water table and dissolve to varying amounts. And then we have these common L NAPLs, these things that float on top. And again, we're going to talk about some of these today, including benzene and toluene, which are two of the three BTEX chemicals. And so it's like I say, it's important to recognize that there are a range of behaviors, even if we call something a NAPL. So I have a few other slides that just show you some scenarios about how NAPL distribution in the subsurface works for both L NAPLs and D NAPLs, and the complications that are found and that affect how we remediate, how we model, excuse me, the migration of those materials. So that you can see here in the saturated zone, right, we have some amount of the NAPL that is dissolved, and it's going to have some kind of interaction of the water with the grains. There may be some binding on the particle surfaces or not. We can also get an emulsion, a small divided sort of particles, or they're really spherules of liquid, D NAPL or L NAPL that move with the water flow. We can also get wetting of grain surfaces where our NAPL coats the surface, and that may have the effect of impeding other chemicals that would like to bind to particle surfaces, making other chemicals in the subsurface distribute more quickly or not be retarded as greatly. So sometimes introducing a NAPL into the subsurface will release other contaminants because it affects this ability for binding. We also have zones where there's a complete saturation or nearly complete saturation of the NAPL kind of replacing water. And then we have up in the aerated zone places where we have a little bit of NAPL and a lot of airspace, and that's where our volatilization is most intense. And this is basically just a model of how that looks, two different scenarios. One where we have a really simple L NAPL case where the soil is one type and it's very homogeneous in grain size. And so this is the amount of NAPL compared to what it could be at saturation. That's the water table down here. And this is the NAPL sitting on top of it. And this is a model of what we might expect to be the concentration, highest concentration kind of at the top of the plume, decreasing as we go down. This is a more complicated scenario where each one of these numbers is a different pathology in the subsurface. So that once we get into complicated compositional variations in the subsurface, then our distribution of NAPL can potentially follow, making it more complicated to remediate. And so I have a few more slides that kind of just go into the details. I'm going to go through them quickly, but if you want to look at these in more detail, you can, which is the distinction between what makes a NAPL be mobile or immobile in the subsurface, meaning is it able to migrate or not? And the essential difference is that for a NAPL to be mobile, it needs to saturate the subsurface, replace all the water. And if it does that, then it can flow just like the water. It may have a different viscosity, it may have a different density. It does have a different density than water. So it may not flow at the same rate, but the same characteristic patterns of flow will govern in the saturated case where water is completely displaced. When we get to immobile situations, it's where we have not as much NAPL present. So we have a mixture of sort of pockets of water and pockets of NAPL. And of course, this is more intractable in terms of cleaning up, but less of a problem in terms of moving around in the environment. This is another scenario showing you a leaky surface storage tank. And again, just how DNAPLs distribute through the subsurface and how volatilization plays a role and how disruption of the chemical plume by these kind of less permeable or denser areas within the aquifer can affect the distribution of the materials. And the one thing to notice is while the groundwater flow is going this way, and the amount of material that is slowly dissolving is also going with the water flow, since the base of the aquifer is flowing this way, and this DNAPL is flowing on the basis of density, the DNAPL that isn't dissolved in water can flow in the opposite direction of the water flow. These are just a few more scenarios that kind of show you different conditions of DNAPL release and where we find undissolved DNAPL and the kind of contaminant plume. And I know these diagrams aren't easy to read, but this kind of hashed pattern is dissolved, and this black pattern is non-dissolved. So we'll find the dissolved and non-dissolved components in different places. These are just a couple of other scenarios. And in this case here, again, because we have a perched aquifer with a sloping base on it, even if groundwater flow is going this way, this material can flow in the opposite direction because it's following the base of the aquifer. Okay, so that's DNAPLs. Now I want to go more broadly, talk about something that we talked about earlier in the semester. We talked about organic chemicals, which is to think about what makes a chemical migrate in the subsurface or change into something else or not. And so this is kind of the topic of reactivity and mobility. And I think, as you can imagine, chemicals that are mobile, that dissolve in water and or float on the water table or sink to the base of the water table and move around a lot are going to be distributed into the environment. Sometimes distribution is exactly what we want because there's dispersion and dilution, and this is the simplest way to remediate some contamination. But other times it can be really problematic, especially if we have spills or leaks that are just upslope of sampling wells that we know we need to take the water from. So we want to know something about whether chemicals migrate. We also kind of want to know, well, how reactive is something in the subsurface? Does it just sit around or does it change into something else? And the reactive contaminants, sometimes they react to things that are less hazardous, but sometimes they react to things that are more hazardous. So we kind of want to understand those characteristics. And reactivity in this case includes both abiotic or inorganic chemical degradation pathways as well as microbially mediated. And in some cases, microbially mediated degradation is favored in aerobic conditions, and in some cases, anaerobic conditions. So when we talked about organic chemistry, we talked about how molecules change in the presence of oxygen or the absence of oxygen, and this becomes important. It becomes important not only in understanding fate and transport in a particular environment, but if we're going to remediate, sometimes we want to encourage this degradation. So we may inject oxygen into the subsurface, or we may inject hydrogen into the subsurface to keep it reducing, depending on the contaminants that we're looking at. So, there's a lot to know about the chemicals in addition to all the stuff that we talked about last time, which are the conditions of fluid flow. So if you look in your reading for the end of last week and this week, or today at least in chapter 6, you'll see there's a whole bunch of detail about different organic chemical classes. And I'm not going to try to go through them here. I think the book does a really good job. You should at least skim through them. I don't want you to memorize anything, but I do emphasize that you should be able to look at a chemical structure and say something about the material's affinity for the solids, meaning do they want to bind to it by Lewis acid, Lewis base interactions, and how water soluble are they? And we talked about the water solubility characteristic when we talked about organic contaminants and chemicals earlier in the semester. If you remember, I had a group that were really water soluble, really water soluble. You can use those as a guide to help you understand which chemicals, especially in a mix of chemicals, do you think are going to distribute with the water because they're dissolved, and which ones aren't. So we did want to highlight a few. This is a group of chemicals I introduced to you in lecture 8, the BTEX chemicals. I'm just showing you them again. Benzene, which is just this chemical here. Toluene has a methyl group. Xylene has methyl groups and 2 methyl groups in 3 different places. And ethyl benzene is the E. It's not shown here, but that would be 2 carbons that's sticking off. This group of chemicals is commonly found in contamination in a lot of different places because it's feedstock for a whole bunch of different industrial production processes. So we see it where plastic is being made, where pesticides are being made and used, where synthetic fibers like nylon and polyester and so forth are being made, as well as associated with gasoline. And so these chemicals are introduced into the environment in a mixture of other chemicals, but they have a fairly unique chemical profile. They're fairly reactive, and so it's sort of important to illustrate what they do in the subsurface. So they degrade really quickly, and they degrade by mechanisms that decompose oxygen. So in settings where we have a lot of BTEX contamination, we can get degradation and pulling ourselves down the redox ladder to low oxygen concentration, not from a biological oxidation demand, but from a chemical oxidation demand, which is basically the same thing. It's just that the degradation happens in the absence of organisms. Organisms in the subsurface can also kick in and take over once the oxygen is decomposed and further break these down. But they break down relatively quickly, but not all at the same rate. So a chemical plume of BTEX chemicals will change in composition of the relative proportions of chemicals in the subsurface because of the rate of breakdown and who's doing the breakdown. So this is a series of injection wells along, or monitoring wells, I should say, along a 1 kilometer transect downflow right at a contamination site, which is what the 0 is. So it's every couple 100 meters. And so you can see up here the concentration of various things. So here's the BTEX chemicals themselves, and you can see that the concentrations decrease, but for instance, this form of xylene decreases more slowly as we move down gradient. We can look at some of these other chemicals that are used as electron receptors as part of the degradation process, and we can see some interesting peaks, right? Like here's the oxygen is decreasing, but here's the iron going up, right? So there's some kind of iron reduction happening once the oxygen is gone away. And if we follow this line all the way over here, this diamond, now we're starting to see sulfate occurring in even some methanogenesis. And so that tells us that the redox ladder is happening. We can also look at total BTEX carbon, the total chemical oxygen demand, and the amount of dissolved CO2, and we can see that these 2 things go down where that thing goes up as we go down. So we know the chemical reactivity going on And we suspect because of these chemicals increasing downflow that there's also biological risk. And so this is sort of two diagrams. This one over here is sort of incubation in time and days on both axes. These are the different chemicals of the BTEX group. And you can see some of these chemicals don't break down very quickly in time, and others of them do break down quickly. And if we look at the difference between soil samples that have live iron reducing bacteria in them and ones that don't, we see a difference where the ones that do have live iron degradation have a faster rate of degradation than the ones that don't. Okay, another classic chemicals which we talked about before, the polychlorinated hydrocarbons is a huge class, goes from small molecular weight to large molecular weight ones. I showed you this slide before. DUT, DED, DDE, these are degradation products of that. Lindane, there are also simple molecular compounds like vinyl chloride, trichloroethylene, perchloroethylene, et cetera, et cetera. They're used in a ton of different materials. Again, in industry, adhesives, flame retardant materials, pesticides. And one of the interesting things about some of these chemicals that were designed to be used for specific application in the environment, especially pesticide, is they're usually designed to have certain characteristics that keep them in place doing the work of the pesticide, meaning they tend to be water insoluble, they tend to be fairly volatile, they tend to have something called a high lipophilicity, which we'll talk about in a second, which is what makes them easily absorbed by organisms, which put them in the category of really bad from the contamination perspective. So next time we're going to talk a little bit more about lethality and what makes a chemical hazardous or not. But I wanted to illustrate for you that we talked about lethal doses before. The lethal dose of DDT and aspirin are the same, right? It takes about the same amount to ingest and die from it. The difference is that this molecule, if you receive it all in one dose, and this one all in one dose, and you get a lethal dose, then of course that will be fatal. But because this chemical is not soluble in water, it dissolves in the fatty tissues of the organism, you can get a small exposure over a long period of time, and it will build up to a lethal concentration. It may take many decades. The difference between what we call acute and chronic exposure, whereas this chemical is very water soluble. So that if you get it all at once, yes, you get a lethal dose. But if you get small doses over time, it's both water soluble and easy to metabolize, so it keeps being flushed out. So you never reach a lethal concentration in the body. And so it doesn't take that high of a lethality of a chemical to decide whether or not it's going to have impacts. It has more to do with whether or not it accumulates in the body and how soluble it is in water and or being able to be flushed out. So this is just a little bit examples of how halogenated hydrocarbons can be decomposed. There's a bunch of different mechanisms that are involved in sort of breaking open of a benzene ring, oxidizing it, and ultimately breaking it apart to straight chain, organic. In this case, this is a carboxylic acid, and we've lost the halogen. You can get all sorts of different kinds of reactions, and you can find both reducing and oxidative mechanisms, but it's more common to find halogenated hydrocarbons breaking down in reducing environments. These are just more pathways, and again, I'm not going to try to go through all of them, but you can see here this molecule has 4 chlorines on it. 2 of the chlorines have been removed, and it's now got a carbon-carbon double bond. That is a reducing mechanism, and this can be further broken down. For instance, this chemical, vinyl chloride, which was one of the famous chemicals associated with the train wreck last month in East Palestine in Ohio, it does break down to ethylene. It's fairly volatile because it's only got 1 chlorine, but it's a fairly toxic chemical, and this rate of degradation is pretty slow, especially in oxygenated environments. In reducing environments and subsurface, it can be accelerated, and we'll talk about how we do that. in a couple of moments. And these are just some other mechanisms through which, by reduction and or hydrolysis, we can take halogens. Remember, halogens can be depicted by the letter X. Organic molecules, meaning they can be fluorine, chlorine, or bromine, to a lesser extent iodine. And you can see in all of these reactions, we're removing the halogen and producing a different kind of organic molecule that's generally more soluble in water. Another class of organic chemicals that's useful to know about are the pyrethrins. Pyrethrins are a class of molecules that are characteristic of having this cyclohexane ester, where there's a carboxylic acid and then this is an R group. There's two common forms of the chemical pyrethrin that are distinguished by having this methyl group here or this methyl ester connected to it. But this molecule and molecules like it are the structural kind of analogs of a lot of healthy or natural alternative fertilizers. I just also show you the structure of nicotine. It's a similar shaped molecule, just in case you're interested. These three chemicals are all common in sort of, kind of more organic and less toxic pesticides that you can apply in your garden. They're much easier to break down. They're not nearly as fat soluble. They're not nearly as volatile, but they're highly water soluble. So they wash away really quickly. And that means that they're less effective when used in a place, but that also means that they can distribute into the environment with the free flowing water. So we want to kind of categorize chemicals on how much impact they have in the subsurface on the basis of things like how soluble and reactive and volatile they are. But another really important aspect of chemical toxicity for organic chemicals is what we call the lipophilicity. The lipophilicity is how much does that chemical want to dissolve in fat. Those are the kinds of chemicals that build up in your body or other organisms' bodies and persist over time. Many of the toxins that people tell you to be concerned about when eating things like fish, those are also highly lipophilic chemicals that they build up in the organism over time. And some organisms can detoxify it so that it's not toxic to them while they have high concentrations. But when other organisms eat that flesh or the fatty tissue or whatever, they can become exposed to it. So one way to determine lipophilicity is using the N-octanol solubility rule. So N-octanol is a straight chain organic alcohol with 8 carbons on it. And think about the similarity of the name to octane, the component that's used to rate gasoline, organic carbon richness. This is an alcohol. And what we find for a whole bunch of different organic chemicals is that if it's really soluble in water, it's got a really low N-octanol solubility or lipophilicity. And if it's really insoluble in water, it's got a high value. So think about NAPLS that we just talked about, or some of these other organic chemicals. The ones that don't dissolve in water and distribute very far and wide are more likely to be bioconcentrated in organisms. And I say next time we're going to talk about the difference between what we call bioaccumulation and biomagnification and the impacts on ecosystems of their introduction. And in some ways, these chemicals are sort of right up the middle. They're a little bit soluble in water, so they can be distributed a little bit, but when organisms come in contact with them, they're moderately lipophilic, so we have sort of the worst of both worlds. They can spread and be bioaccumulated. This is just an example from another paper from a small number of subset of chemicals from here, PCBs, hexachlorobenzene, carbon tetrachloride, found in the solubility and the concentration in the tissues of trout. And you can see again the same kind of inverse relationship where the chemicals that are rate high on this scale over here also rate high in how concentrated they are in the organism. So as you can imagine, a lot of chemicals will change their characteristic in the subsurface by being reacted upon. there are also things that scientists do to try and keep the good or the useful, I guess I would say, aspects of chemicals, but reduce their toxicity by changing around the chemical a little bit. So this is the example of DDT here, where R1 and R2 would be chlorine in DDT. And you can see the ecological magnification, the concentration in a fish relative to the concentration in the water that it's living in for pure DDT, 84,500. If we replace these, right, if we replace them with methoxy groups, that goes down by like a factor of 80 almost. And if we replace them with this, sulfoxy groups, then you can see it goes down even more. Now, this is one way of taking these chemicals and making them still be effective in the environment and perhaps not as toxic. But there are other alternatives and other ways of doing things as well. But also realize that when these chemicals are broken down, things can happen to them that can make them more or less toxic, depending on what's being taken off the molecule, what's being replaced. And it all kind of goes back to, at least, maybe not all, but significantly to that lipophilicity factor. Okay, so now I just want to talk a little bit about some of the contaminants that we find here in Hawaii. And I just want to remind you about how the groundwater shallow aquifers are distributed on the island of Oahu. And so up on the North Shore, there's an aquifer that kind of drains from the kind of highlands to the north. There's this high level aquifer on the Schofield Plateau, which is affected by all the sort of development that happens up in this area. There's this kind of Pearl Harbor aquifer, and it with an imperfect and not complete boundary into what's called the Honolulu aquifer. And one of the important things about how water gets into these aquifers is by recharging in through the rocks in the co'olaus, especially rocks, dike rocks that allow water to flow downward and then distribute into these kind of aquifers that are bounded by various lava flows and more or less permeable composition. So most of that water discharges out towards the coast. These discharge this way. This discharges into Pearl Harbor and or the Ewa Plain. This discharges basically down into the Pearl Harbor. So contamination in this one shows up here. There's also, small aquifer obviously on the shore. And so relative to those aquifers, we also can think a little bit about the land use practices. And so on this diagram, all the areas in black are areas that are developed, urbanized. You can see in green the forests, and blue the kind of wetlands. Yellow is what is being used for agriculture. Red is what used to be used for agriculture, kind of going back to 1980. So as you can imagine, you might expect to find, as a function of different aquifers, the way they flow, and what the land use practices were currently and in the past, different chemicals where we have agricultural activity, industrial and military activity, and kind of whatever you want to call it, urban environment. So this is just a few contaminants found in Board of Water Supply wells. So each one of these dots is a well, and the dots that have a positive indication, you don't have concentration information, it's just more of a yes or no, was it detected, all the red dots. So chlorinated solvents found very highly associated with especially the Schofield aquifer, but also this region over here on the east side of Pearl Harbor. This is fumigants. Fumigants are primarily used in agriculture, whereas the chlorinated hydrocarbons, they have their uses in agriculture, industrial, jet fuel, various military applications. So more, but you can actually see more occurrences of this in the water than you have, of the halogenated hydrocarbons. This is pesticides, and you can see now there's basically two different ones here, atrazine and dieldrin. And so, and if you get a red dot, it means that you have both. And so you can see here, atrazine showing up over here. Atrazine was common, employed in the sugar and pineapple industries, and other chemicals here, dieldrin showing up in a lot of places, including, in Manoa Valley and Paloma Valley. Rice, which used to be cultivated in those valleys, used dieldrin, for instance. And so of the three contaminant classes we've looked at so far, this urban Honolulu looks pretty clean for the first two, but it does show up here. Not at toxic levels, but at levels that indicate that it's present. Okay, so that's just like a little snapshot. There's obviously a lot more we can talk about that if we want to. But I just wanted to mention now the leaking fuel situation at Red Hill, which has been evolving very quickly over the last few years. But just to kind of, if you haven't followed the news or not really aware of it, the Red Hill storage tanks are these huge underground structures that were built right after the Pearl Harbor attack to say, we're going to store our fuel underground so that they can't, if an enemy attacks us, they're not going to be able to bomb it or take away the fuel supply that's needed for the planes and the boats. So it's this network of really large underground fuel tanks that built upslope in Moana Valley. And the idea was that they were meant to gravity feed fuel down to Pearl Harbor, right, through big pipes, basically. And the issue is that these tanks are, almost 3/4 of a century old. So they degraded. It's actually a pretty ambitious design, and for its time, it was really innovative, but they haven't been repaired or fixed, and they're cracking and they're leaking. And the leaks were first identified about a decade ago. And you know how this kind of story goes, where it was found in some water. It was water that was actually feeding people that were in housing, military housing. And, this kind of standard response of the military in most of these cases is to sort of like pretend that it's not happening or deny, and then go in and say, okay, we'll do something, but not really do very much. And it's only when it got to the point of migrating out of the military housing and becoming aware to the State Department of Health and the Environmental Protection Agency that people realized that something needs to be done to at least stop the leaking and then decide if there's concentrations that are high enough that need remediation, or to just allow dispersion and flow to kind of distribute stuff. So there has still, to this day, been a lot of debate about what is the rate of spread of the chemicals in these fuel components, which include things like the BPEX chemicals. How fast do they degrade? How can you repair the site? This is a subsurface infrastructure that's pretty hard to get to, especially without draining them out. How do you remediate the water? What are the risks to the Honolulu water supply if that contamination, for instance, manages to get itself all the way into, so that setting is kind of right up in here. If it gets into the lower part of the aquifer where there's flow that basically goes from this direction south, it could show up in a lot of the distribution network. And most people don't believe that that's where it's going, or not right away, but it could. It's something that we at least need to think about. And so, it's a very complicated issue. I don't want to kind of minimize it. It's multi-jurisdictional. You've got the state, you've got the military, you've got the Environmental Protection Agency, you've got all sorts of individual stakeholders, environmental organizations, and Native Hawaiian organizations, and kind of watching them work with each other to some extent, or work against each other to some extent, has been interesting, illustrative of some of the problems that impact how remediation takes place. So this is where Red Hill is, just so you can kind of see the location. And this is kind of what it looks like. This was dug into the volcanic rock. And like I say, it was a very, very ambitious. So these are the pipes that drain from the storage tanks further upslope. This stuff feeds by gravity down towards Pearl Harbor. And so if you're going to get rid of this, you need to have another place where you're going to store petroleum and jet fuel and whatever other stuff they have there. And this is kind of what the concept was, these big kind of buried capsules, and this is what they look like. And these things are huge when they were being built. Those are people like this, right? And so these are gigantic concrete capsules that if they were built today, they'd be designed differently. They would have concrete that is able to withstand some changes in heat and temperature and ground shifting and not crack. They would be lined. They would have metal infrastructure that's holding it together, rebar that doesn't, degrade and oxidize and rust. You have to remember, this was like, built in whatever, the late 40s and the early 50s. So it's, different era. And so this is the site. These are the bunkers. This is where they're kind of arranged like this. And these are a bunch of different wells that were sampled, and the kind of area where stuff does and doesn't show up. So this is all kind of U.S. military housing right outside here. That's Halata Correctional Facility on the other side of the valley. And so, the question is how much in each of these wells is showing up, and it has shown up different components in different parts of the system over time. And this is just an infographic from the Navy, kind of showing, well, here's how we think the remediation discussion should unfold. So you've got these kind of three primary stakeholders, right? Coordinators that come from the State Department of Health, Environmental Protection Agency, and the Navy. And you can imagine that, it looks great on a diagram, you may not always get complete crosstalk between these three, smooth crosstalk. And then there's, a lead organization, which is, people that have been assigned from the Navy to do this as a project team. There's consultants, there's people who are out in the field, there are people who are modeling, there are people that are taking water samples and measuring their compositions and modeling the data and validating the data. All of these things become not just sort of academic exercises, they affect the potential to spend, hundreds of millions of dollars on this remediation effort. And these are the kinds of things that, an environmental chemist might slot in down here, right? You're given a job and given an assignment to do something. What they decide to do with that information is different. So this is, I think, a particularly useful infographic, and we realize it's kind of small. This is from a few years ago from the Sierra Club. And it kind of explains what's the story with these tanks and what are some various ways to fix them, right? And these various fixes include different amounts of cost and infrastructure and downtime. So one idea is to completely drain them and then to reline them. Another one is to drain them and stick a new material inside of them. Others are to move them. And, as of last year, it was decided, this is all too expensive. We're just going to stop putting fuel there. And people here were really happy. The only thing is that, having the Secretary of Defense say, yes, we are not going to, we're going to shut this thing down, doesn't mean they're going to shut it down tomorrow. It's still not shut down. There's no plans for shutdown. And saying that you're going to shut it down doesn't say how are you going to affect the contamination that's already in the environment. What's the remediation plan? And, a state like Hawaii is a relatively small state. We're not really provisioned to deal with Superfund level remediation ourselves. We need help. We need the Environmental Protection Agency, and we need financial resources, or all of our taxes are going to go up by a lot. And this is still the thing that they're talking about. So at least we know that they're going to build some fuel tanks somewhere else, and they're going to eventually drain these things. But now there's this big discussion about, well, how are they going to drain them? When are they going to drain them? Where are they going to put that stuff? How are they going to drain them in a way that doesn't cause collapse of those structures and more contamination of the subsurface? So things have shifted, but I expect that we'll probably be talking about this 10 years from now, right? This is a long-term problem. Okay, so that's that. Now let's talk about remediation in general for the rest of the time today. And we want to do a couple of things. We want to talk about strategies for remediation in light of all the stuff that we've been talking about: volatility, solubility, lipophilicity, NAPL versus DNAPL, all those kinds of things. And there's different categories of decomposition or remediation. And each one of these can have its benefits or its downsides depending on the site and the contamination, but also they cost different amounts. Right? And so sometimes, even though you know something is the gold standard, if you don't have the money available to fully clean up the site using the gold standard, you try one of these other methods first and see what you can get. So these are kind of 4 general categories. One category of remediation is to try and have decomposition in the ground of the contaminant. And this can either be natural or aided by human activities. You can also have what we call on-site decomposition. What this means is that we pump water out of the ground and we pull with it the contaminant. And then up on the surface, we have a series of tanks that are used to decompose the pumped water. And there's a whole bunch of different things that can happen. But for instance, for volatile organic carbon compounds, one thing that is done is to bring water up and to aerate it and to release into the atmosphere. Sometimes the contamination is so intractable that it doesn't degrade enough or fast enough on site, and you can't even really pump it out with the water. And so in this case, you have to remove the stuff from the ground. And this can be done, again, by pumping like a solvent or a surfactant into the ground, sucking it out and then trucking it away to somewhere else. And the kind of most intense remediation is to remove the contaminant and the substrate. Just come in there with a backhoe and dig stuff out, pull all the contaminated soil and the water out to another place. And this is obviously the most expensive, the most disruptive to the setting. And but in extreme cases, this is what needs to be done. And then this stuff will be taken somewhere else and contained and buried, and hopefully it won't migrate. So of those different kinds, we have to consider some of the processes that happen in the subsurface. One of them is the process of attenuation, right? So this is a diagram of time versus distance down gradient of a chemical contaminant plume, kind of high, medium, low concentration and distributing. And if it's a point source contaminant and it's not a continuous source, like a leaky underground tank, let's say it's a spill, like from a train car or something that isn't continuing to happen, then with time, that will migrate with the flow away from the point of where it was first introduced. And because of dispersion that we talked about last time, the concentration will go down. So sometimes just waiting and watching the plume is all we have to do. But one of the requirements is that we don't have a continuous source. If you've got a leaking source that's continuing over time, it will disperse and it will attenuate, but it's not going to migrate away from the original point of introduction. So the pump and treat method, which I mentioned before, this is kind of what it looks like in reality. These are 3 different examples of tanks being installed. These right on the surface, as well as those, these sort of housing and pumping water into the subsurface. And that can either be pure water or water with chemicals added to them that will help remove contaminants. That water gets pumped up into a closed loop into reaction chambers. Reaction chambers do their job, and then that water gets reintroduced into the subsurface as a cycle to sort of pull things out. This tends to work best in areas where the contamination isn't too widespread and the water flow isn't too good. You wouldn't want to get into a situation where you're pumping a bunch of water into the subsurface and pumping it back out and having some amount of your enhanced kind of mobility contaminant leaking out of that system into the rest of the aquifer. So in situ degradation is slightly different. This is where we put chemicals into the subsurface that allow for some kind of chemical reaction to happen in the subsurface. And these can be things for oxidizing agents or reducing agents. Sometimes steam and surfactants are useful. Those are especially useful in the case of NAPLS, things that will help kind of loosen them up and allow them to flow. And this is an example where we've got, contamination in the subsurface. And here we have an injection well where we're sticking in a surfactant in this particular case, and then releasing them from the water and then pouring that water out and treating it somewhere else. In some cases, we have to do a pump and treat, and in some cases, chemicals can be introduced here that will basically decompose most of this stuff. So the water that we're pumping back out has very residual concentrations. Related to that are a couple of other kind of chemical reaction type settings. This one here is something called bioventing, where organisms that help decompose chemicals, petroleum, for instance, can be introduced into the subsurface and allow for some kind of chemical degradation and then recovering of the chemicals on either side. You can also sparge in either oxygen or hydrogen to help enhance chemical or biological breakdown of chemicals in the subsurface. If you want them to be aerobic or anaerobic, you would use oxygen or hydrogen respectively. And these are processes that just help speed up the rate of degradation. But again, you're generally extracting chemicals back out from the subsurface, especially if you're injecting gas. You want to overpressurize the system. And so, these are all different kinds of methods, and there's variations on these themes. And if none of these work, then you have to go to this kind of remove and treat, where you pump stuff out and treat it on the surface or somewhere else. So the very last scenario, the kind of worst one, which I mentioned on that prior list, is this sort of pump and remove, where you pump stuff out of the ground, or if it's not pumpable, you have to remove everything from the ground and take it to another site for decomposition. And this is basically an example of a DNAPL at the bottom of an aquifer. This is very permeable material with high hydraulic conductivity. This is a moderate permeable material. Water would flow through it, but DNAPL is not able to. And so we've got this pool of DNAPL. And in essence, this is in this particular scenario, chemicals are put in here to help make this flow a little bit better, and then it's sucked out and taken somewhere else. This is expensive. Okay, so this is just a table from the EPA of the 25 most frequently detected groundwater contaminants at hazardous sites. And I've highlighted them by category. They're not highlighted on the site, but things that are in blue are halogenated hydrocarbons, trichloroethylene, tetrachloroethylene, which is PCE, methyl chloride, trichloroethylene, chloroform, et cetera, et cetera. These are all halogenated hydrocarbons. Here's the famous vinyl chloride. And then the things in red are the BTEX chemicals, so we also just talked about today. And then the stuff in green are heavy metals. So you can see that the vast majority of the contaminants, the most common contaminants, are organic contaminants. We do have heavy metal contamination, and we will get to talking about them as well, but these are a big category, the organic contaminants. So I wanted to spend the last bit of time now talking about a remediation technology that's a little bit different than those categories I gave you. In a way, it's in situ degradation enhanced by the introduction of a human structure. And the human structure is something called a PRB, which stands for permeable reactive barrier. And these have been around since about the start of the century. They were, when they were first kind of put in use, there were people that were a little skeptical about them. But ultimately, I would say it took about 10 years for people to realize that in some cases, this is excellent. In essence, what you're doing is digging a trench that intersects the groundwater flow, putting in chemicals that water will flow through and react with, so that on the outflow side, you're getting remediated groundwater, which is kind of what's shown here. Here's a leaking set of storage tanks on the surface, and it can have a range of chemicals. It can have organic chemicals, but it can also have inorganic chemicals that can be immobilized or changed in composition by oxidation or reduction. And ZVI stands for zero valent iron. And so the simplest kinds of permeable reactive barriers reduce contaminants by using iron. You can do fancier things, you can add other things to the iron, just the rate and so forth. But that's the basic gist of it, is introducing something in the subsurface. So I showed you this diagram once before of the kind of all the different types of remediation. We talked about phytoremediation a few times ago. This, a PRB, kind of fits in this category. It's a catalysis for speeding up degradation mechanisms of contaminants in the subsurface, pretty much not biologically, just chemically. And they can either be oxidative or reducing mechanisms depending on the contaminants in the situation. So this is just another example, a set of examples of what the PRB looks like. So this is a plan view. You've got a contaminant in a plume. The plume is spreading this way. It intersects with the PRB, and it's engineered in such a way to give sufficient time for the chemical that's in the water to interact with this permeable substrate, decompose those chemicals, and send out remediated ground. So as you can imagine, this would work pretty well if we have a point source of contamination and we can install the barrier pretty close to the source. If we have to go pretty far downstream and it's dispersed or our contaminants spilled over a very large area, then the PRB has to get very, very large, and that may not be effective anymore. But there are things that can be done in the subsurface. This is called a funnel and gate, where basically once a plume has dispersed a fair amount, you can sort of redirect the flow just to a part of the structure, that's the PRB, to kind of remediate the composition. So this doesn't always work. Here's some conditions where, they work best when your landscape is stable, where they're close to the contaminant source. You need it to be below a certain water flow threshold. If the water is racing through, that's very difficult. And any kind of predictable water flow patterns. And so you can ask, well, why do we use reduced metal or zero valent iron? And it's basically because the reaction of iron 0 to iron 2 and iron 2 to iron 3 is releasing electrons, and those electrons are allowing for the decomposition of some contaminants. And I don't know why I have this in here twice, but one thing that you can't do is add other chemicals into the iron, like palladium. Makes it much more expensive, but can increase the rate of reaction. So these are three mechanisms where, because of the flow of electrons, you can break down halogenated hydrocarbons. So RCl turning into RH, and the way in which electrons that are available from the degradation of the iron, zero valent iron, give us the electrons necessary to do this chemical breakdown. And as I see, there's just three slightly different mechanisms here that operate either directly on the chemical or on water in the subsurface producing hydrogen, which then operates on the chemical. But the point being that the barrier itself eventually becomes oxidized and needs to be replaced, but we are taking, in this case example, halogenated hydrocarbons and turning them into regular hydrocarbons, which tend to biodegrade pretty quickly on their own, plus they tend to be fairly volatile. And this is just a table showing you the number of days it takes for a whole bunch of different chemicals to degrade in the subsurface. It's at to the concentration to cut in half. So you can see they're sort of like on the order of 1 or 2 weeks for most of these. There's some chemicals here that take longer, and so you have to control the water flow, or maybe if this is the primary contaminant, a PRB wouldn't be the best thing. And there's some mechanistic information in this table about how different isomers of chemicals degrade at different rates. It is a level of detail you don't have to worry about, but these are like an order of magnitude or more faster than the natural degradation rates. So you can really speed things up. So you can also use PRBs around, former kind of textile mills or organic dyes, or places where pesticides were used. A lot of large industrial farms have something called a poison shack, where they mix up all the pesticides and some of it gets spilled into the ground. We have these scenarios here in Hawaii. And so you can have relatively high concentrations and relatively restricted area. And, you know, I just give you one example here, that if you palletize your iron, you can make some chemicals, instead of taking days to a week, they can break down in a few hours. So depending on what the situation is, it costs a lot more money to use palladium, but it's possible. So this is what a PRB looks like going in. You can see just building a trench. This is a waterway. I think this is on Cape Cod, and that's what the zero valent iron looks like. So from a disruption of the kind of local environment perspective, this isn't too bad, right? It can be done. It's certainly a lot better than coming in and trying to dig out the entire area of contamination. So when it works really well. This is from that same site. This is a river. There's a plume on a military base on Cape Cod where it's got contamination of trichloroethylene and chromium in a plume moving down grade. These are a bunch of wells, monitoring wells, both upflow and downflow of the permeable reactive barrier that was installed to kind of intercept and degrade that plume. And this is kind of what it looks like. This is the concentration of trichloroethylene along one of those flow lines. This is the plume, this is the PRB, this is the concentration coming out. It's not zero, but it's substantially lower. And these are just the location of these monitoring sites. So, these, like I say, this technology is useful and becoming more and more common. This is just another aside. This is, you don't only have to have organic contaminants. You can have chromium-6, which is a highly toxic form of chromium. Aaron Brockovich and that whole story. One of the ways to make it safe is to reduce it to chromium-3. And that can be done, again, by having one of these walls with zero valent iron and reducing the chromium. This is just another look at what one of these permeable reactive barriers can look like. This is a slightly different technology. This is called a reactive fence that is coupled, has reaction zone and monitors. It's specifically for BTEX chemicals. And again, you can see the size relative to people, and it's used to help focus the degradation of BTEX by injecting oxygen and substrates. And the final thing I wanted to mention is that the kind of technology that's used in permeable reactive barriers can be used in other settings as well, including proactively. So imagine if you are developing a brand new landfill, why not put a reactive barrier around the landfill so that the material does start to leach out, it comes in contact with this reaction barrier, and it's less likely to affect groundwater. And that's what this example is of a landfill liner. And they can be used in all sorts of other settings, like I say, proactively when facilities are being designed, where you anticipate perhaps some spills every once in a while. Putting this in beforehand could save money in the long term by giving you one extra layer of defense. And one of the interesting things with the kind of modern day liners and barriers is that they come with sensors that are put in there that tell you when stuff is happening, so you know if certain chemicals are being encountered in the subsurface. So that's kind of organic contaminants and kind of remediation. Are there questions about that stuff? No? Okay. Did you all see, I'm sorry, but I signed a homework yesterday. I should have done it sooner, but I didn't. But hopefully it isn't too hard for anyone. Let me know if you have trouble getting it done by the end of the week.